So I know there's a lot of sessions about AI and Polaris catalog and all this nice semantic layer, but I've been always a database guy, and so I think performance is very critical, right? Like whether it's Oracle or Postgres or Databricks or Dremio, doesn't matter. So I think we definitely need to see why Iceberg matters, and that's because of performance, right? Like you may have all the cool features, but if performance is not hitting your SLAs, then we don't we will not be looking into this, right? So basically, I want to go into a few of behind the scenes, right? Like I want to see why in the first place did we come to columnar? Like a lot of times we straight away jump into Parquet world, and sometimes we don't have the insights into what were the problems that were in the row versus columnar format. Like for example, why can't we do reporting on Oracle or SQL Server, right? I want to talk about that a little bit. Then I want to talk about the actual Iceberg architecture. Polaris catalog does the service, but where does the actual metadata reside, and what is the architecture behind it, right? And I want to go through that, and that will give a very good understanding of how we do partition pruning and predicate pushdown and all that. Then there is a little bit nuance between partition pruning and predicate pushdown. Like both are filters, but like what is the advantage of doing pruning when possible, and what has improved in predicate pushdown over old school Parquet, right? Then we want to talk about a couple of very good features in Iceberg for partitioning, like partitioning transform and partition evolution, right? And then we want to also talk about runtime filtering, which is again another very big performance boost, right? Some SQL engines call it as dynamic filtering, and so I want to go over all this, right? Okay. So obviously, the first thing I want to talk about is take a step back. Before the birth of all these SQL engines, and even before data warehouses, there was Oracle, Postgres, all these old school databases. And why did even the need for all this Iceberg and Parquet come, or Parquet and then Iceberg come? There are other couple of formats you might have worked on is Avro, and then you might have worked on ORC, right? It's a proprietary format from Hortonworks. So I wanted to take a step back and see why we started, thinking about columnar format. So if you typically see a query that comes into, like say from a bank for reporting needs, it's going to be, hey, give me in New York State the borough-wise, like what are the home loans that we have sold, right? So if you actually see that query, we are actually scanning very less columns, right? We may scan, and then we are also grouping by a measure like a count or a sum, right? So if you run the same query on Oracle, as everybody knows, it's going to scan so many rows, right? Because every row contains the column. So whether you're selecting one column or many columns, you're going to scan a lot of columns, right? So obviously, but in case of a columnar architecture, which was Parquet, Avro, and ORC to start with, and then you come into Iceberg, it is stored in columnar format. So the scan is like super efficient, right? So like that's like a basic understanding I wanted to give. And obviously the data layout, right? Like obviously in OLTP databases, it is row blocks versus in Iceberg, it is column chunks. Obviously I have a typo, optimized for transactions, right? And so you go on Black Friday sale and you go buy something in Amazon.com, or you go buy something on BestBuy.com. There's no doubt Oracle is probably the best database for that. You go, there's sequential inserts, right? But if you want to go and report on how did Best Buy do in the 2025 Thanksgiving Black Friday sale on 65-inch Sony OLED TVs, right? That is a very specific analytical query, and obviously Iceberg is the right candidate for that. And then obviously for reading, you need both needs columns, and the best part is the compression on the columnar format is way better, right? So highly optimized. So just a quick snapshot of again on why we are in the column format world is Obviously, it's very inefficient for analytics, the row format, because most queries scan a few columns, but they are spread across so many rows, right? There is excessive data reads, right? Because queries must load every column, because every column exists in every row, right? And the compression efficiency is very, very limited. Am I talking too close here? Okay. For a columnar format database, obviously there is selective reading. We only read only the needed columns, so it reduces the I/O massively. And obviously I/O is the most expensive, right? When we spill to disk, we know that it is slow, so we want to reduce I/O massively. We want better compression, right? Like, that way, it's yielding high compression ratios. And obviously, CPUs can also process batches of values, so the vectorized execution is highly efficient. So that was a little background into why we came into Iceberg in the first place, right? Obviously, Parquet and then Iceberg. So now I want to change the focus a little bit into what happens behind the scenes when a query is fired into any of these SQL engines that support Apache Iceberg, right? So obviously, like when Mark was talking about, he was talking about the Polaris catalog, will tell you where the table is. But the actual metadata at the manifest list, at the manifest files, I'm going to go over each of these independently, if it's new jargon for you guys, all resides in the object store. So it could be S3, it could be Azure Storage, or it could be GCS, right? So what does the metadata file contain? The metadata file contains a list of snapshots, and every Iceberg, whether it's an insert or adding a row or deleting a row, will produce a snapshot. And the metadata file will also know what the latest snapshot is, so that it can give the most current data, right? So that's where it starts. So the line above the dotted line is not in the object store. It's probably in a local key value store. In case of Dremio, it's on the coordinator on a local KV store, right? So that points to the latest metadata file, which again picks the latest snapshot. And as you can see here, it goes and reads the latest manifest file. So the latest snapshot will always have a one-on-one mapping with the manifest file, right? And that is super important, because if you see S0 may go to the old manifest file, but we would never go to S0. It will always go to S1, and S1 would go to the latest manifest list file. What does the manifest list file contain? The manifest list file contains the paths to different manifest file. Not only that, it also contains the max and min partition values on each of these manifest files, right? So it contains two important pieces of information: the paths to the manifest files, and each manifest files what max and min date. For example, if effective date is a partition column, it'll have the max and min of effective dates in each of these, right? So going down that, what does these manifest list file? Oh, by the way, these are Avro files. The manifest list file and the manifest files are Avro files. So what does the manifest file contain? The manifest file contains a list of a set of data files. Obviously, you can see there are multiple manifest files. So this manifest file, for example, will contain the paths to different data files. Not only that, it contains the max and min of partition and non-partition column values. And why I'm stressing on non-partition column values is we'll see that later on why. So obviously, manifest file has some extra information, the paths to the data files, and also the max and min values of all the columns, right? So what happens during a query path, right? So we read the latest snapshot, we come into the manifest list file, and if, say, the var clause has where effective date equal to January 1st, 2025, then what would happen is it would tell which of these manifest files has that information, because it had max and min of each of these partition values, right? So obviously, there's a first level of pruning, right? So it will already prune that it need not read these two manifest files. So that's the first level of pruning, even before it starts reading the data files, right? Then what happens is it comes here and actually reads the path to the data files, but only one of them may have January 1st, 2025, and it goes and reads the partition values in each of these data files and gets and prunes these two. So you're pretty much traversing down the lane and reading one manifest file and one data file. And I'll show you some examples on Dremio in a bit. Cool. So now that we understand partition and non-partition, let us go through a couple of quick bullet points. And I also want to touch Parquet, but if somebody's still on Parquet and, what is the need to go to Iceberg, right? Obviously, there are other things like, DMLs and, going back to an older snapshot, but just for performance-based, right? So obviously, pruning manifest files when reading the manifest file, we talked about. Pruning data files when reading manifest files, we talked about. For non-partition columns, because we are storing the max and min for non-partition columns, it can actually skip data files based on the filter values when reading manifest files. So for example, right, there's a column called name, and it's not a partition column, and same name equal to Dremio. Then the manifest file actually contains max and min of that name column, and it can actually start not reading some of the data files and skipping those data files. But in Parquet, we only store the partition values in the max and min of partition values. So you actually have to open the Parquet footer while reading the data file to actually see if the max and min value exists in that file. So it's a much later stage, and there are way too many files at that point, right? So you have to go through every file. So sometimes customers' dashboards, they may not even contain partition values. It is what it is, right? They may only say, hey, give me all the, state-wise, group it by certain column for where non-partition column equal to blah, right? In that scenario, you would actually be spending a lot of time reading these footers, right? Cool. So let's go to the next slide. Let's talk about partition transforms, right? So we learned why we needed Iceberg. Then we also we learned why we actually, why querying Iceberg is very beneficial when using partition and non-partition column values. But there is another bigger problem in legacy columnar formats like Parquet, where once you decide on a partition and your workload changes and your workload pattern changes, that you have to repartition it on the same column but at a different granularity, you pretty much have to drop everything and recreate, right? So that's a known big, kind of an overhead with Parquet, right? But what happens in Apache Iceberg partition transforms is it's basically hidden partitioning. So you basically can start your go live production on, say, doing on a month of a timestamp. And so for every month, there'll be a folder created on your object store. And so all January data will be stored under one folder, February, and so on. And if you go query, hey, give me all the orders state-wise for January, it would just go read the January partition, right? But then as time builds, data is increasing. And now you may think there are way too many files under the month partition, so I want to switch to a day partition, right? And that is impossible to do in Parquet or old school Avro or ORC. You have to pretty much drop table, and you have to actually then recreate the table. In Iceberg, it's completely transparent. You no need to specify partition columns in queries. Iceberg handles the pruning automatically. So initially, when you give month of TS, and I'll show you an example how the query will come in, and it'll pretty much prune it, and then you can also kind of change it also, right? And that's the next slide. So what are some common examples of partition transforms? Is you can do days and months of year of a timestamp. You can do a bucket. So sometimes you want a partition on customer ID. And in Parquet, that could be too much of overhead because customer ID is too high cardinality, right? So obviously, in Iceberg, you can do a bucket of, so it would create like 100 buckets and spread them over. So you're not going to read one partition, but you're also not going to read millions of partitions. You're going to reduce it, and you can increase this based on how you want to partition, right? And there is truncate, right? You can use truncate. So you can use like group by $10 ranges, And then obviously this is the same example as the month, right? So there are broadly 3 categories in partition transform. So how is it much more, how is it much more efficient than Parquet is obviously no user burden, right? So if you have a partition transform on the month of timestamp, then you actually pretty much can give the date column and not like worry about giving like, 2024-11, right? Automatic pruning, the backend column is timestamp, but actually you are giving a date column in the order date, and obviously Iceberg will figure it out and it will prune it, right? And obviously, right, same query works before and after partition changes. You don't have to have any kind of maintenance scripts. It's, you don't have to drop and recreate tables. And then this is a topic I was talking about where you can actually start with daily and then evolve into monthly as the data grows, right? Obviously, it's big cost savings because you are now using less storage. You are scanning less number of records. So obviously, your compute costs are less. And you can avoid the small files because if you see here, the bucket of actually hashes it into less number of folders. So you don't have too many small files problem because that we know is a big issue, right, if you have small file issues. And then what is partition evolution? Partition evolution is just an extension of partition transform, which is the example I was giving you, right? Like you want to change your partition scheme on the timestamp column from, say, month to day, right? So if this was like traditional partitioning on, Hive Parquet or something, you have to, obviously, it's a full table rewrite. It's downtime, which is very hard to get in production. Everybody knows that. And then obviously a lot of compute costs, and there's always a risk of data loss, right? You don't want to go drop some wrong partition and you can't even roll back, right? But with partition evolution, it's a metadata only operation. Literally you can do an alter table and then you can go and kind of change whatever you want from months of timestamp column to day of timestamp column. The results are instantaneous. There is zero downtime. And then obviously the query is instant seconds. And then it's atomic and safe because you're only doing a DDL. You're not doing any kind of actual drop. You're just running an alter table command. And behind the scenes, Iceberg will take care of everything, right? So that is, partition evolution. So one other very, interesting kind of optimization I want to talk about is runtime filtering. And runtime filtering is actually very important to understand because sometimes it can differentiate between a report running in a few seconds to actually several hours, right? So let's take a very quick example of a very typical, data analytics query where they're joining a dimension table to a fact table, and there is a where clause on the dimension table on a partition column, which is a partition column on the fact table, and there's a filter value, right? So you're basically joining, orders to customers or something. And what happens is when the query, so your expectation is this query should finish super fast because it's a small lookup table and it should be super fast. The minute the table finishes, you know what are the partition values that it will scan in the fact table and pretty much send it through the hash join into the fact table. So when the fact table starts scanning, it will not scan all records. It will only scan records for the partitions that are sent through a Bloom filter from the dimension table. So if there are 1,000 partitions on the fact table, but the dimension table sends records only for 2 partitions, the remaining 98 partitions will be skipped, not during planning, but this is actually during runtime. So as the fact table scans, it'll start skipping partitions because it knows those values have not come over from the dimension table. What that does is it sends less records downstream to the hash join, which means the join is actually joining less number of records, which is probably the most expensive operation, right? Because join is very heavy on memory, and when it starts spilling, it's going to cause the query to slow down. So because now less number of records are going to the join, you are actually doing everything in memory, and there is no spilling, and obviously it's going to be much faster. So obviously let's go through some very quick bullet points. One is Bloom filter. So the dimension table will kind of do a space efficient data structure built from the small table, and the join keys will be sent over to the join table into the fact table. Filter created at the execution time, and it's propagated to the large table, all right? And then there is early pruning. That is because it eliminates data pruning at partition level, and the same thing, the file level, row group level, and at a page level. So it reads really the partitions that are needed, and under that, what are the row groups, and under row groups, what are the pages. And this is automatic. You don't have to do anything to this. This automatically happens, but then it's a feature that it's good to know that when sometimes your query is not performing optimally, and you have a join in this scenario, then you may want to check if the runtime filtering was effective or not. And it's most effective for fact tables joins with filtered dimension tables. And I just showed you an example of one-on-one, but you could have multiple dimension tables and one fact table, and the runtime filtering can come from many of the dimension tables, right? So I want to show, and then one more slide is there is massive, IO reduction because you are not reading that many records in the join, and you're also not scanning that many records on the large fact table. And then it typically speeds up 5 to 10x of this for selective dimension filters. So less memory means reduced memory footprint, and there is reduced network traffic because there is less data going back and forth in the network. And it's better for so now you can run way more concurrent queries than without the runtime filtering. And obviously it's big cost savings because there's less data scanned, and then it then translates to cloud storage and compute cost, right? So